Okay, chemists, today we are going to look at different types of bonds that atoms form in molecules, and frankly look at how different types of bonds have different strengths and different lengths. That's the theme. What makes a bond stronger and shorter versus weaker and longer. And in front of you, I first have just a definition that distinguishes a sigma bond from a pi bond. A sigma bond is when you have electrons and their orbitals overlapping directly along the axis connecting those atoms. So this happens between any hybrid orbitals, which we're going to talk about in a moment, and any just regular old s orbital. So these are a pair of hybrid orbitals, and when they meet face to face, you get what's called a sigma bond. It's the strongest kind of bond we have. Another bond is called a pi bond, and that occurs only between p orbitals, and it's when they overlap above and below the axis connecting two atoms. So this is a p orbital, and here is another p orbital, and you get a pi bond between the two. And then at the bottom of that chart is a nice summary of all the different types of bonds that we see. So far, we've seen single bonds. That means you have exactly one sigma. A double bond, however, is one sigma and one pi. And a triple bond is one sigma, but then two pi bonds. So what forms these pi bonds and sigma bonds? And also, very importantly, what the heck are hybrid orbitals? Well, hybrid orbitals help us explain the type of bonding and geometries that we see with molecules. So first, let's go back to electron configuration. Here is carbon's electron configuration: 1s2, 2s2, 2p2, drawn in an orbital diagram. Now, if carbon were to form bonds as it does with, let's say, 4 hydrogens to make methane, we would think that would only have space to pair up with 2 other electrons, but we know that it forms 4 bonds. So it's been proposed that the valence orbitals of carbon hybridize, that the atomic orbitals hybridize to form new orbitals. And this is a theory we use to explain the observation. So if we have these 4 orbitals, the 1 2s orbital and the 3 2p orbitals, we can combine them in different ways and get 3 different possible hybridizations out of this. The first one is what you get when you combine all 4 of them, and you get 4 brand new orbitals with 1 electron in each. Because it's a combination of a single s and 3 p orbitals, they call it an sp3 orbital. And the shape of those orbitals is a little bit different than the spherical s's or the dumbbell-shaped p orbitals. They're these sort of lopsided dumbbell shapes. This is actually a hybrid orbital right here, and they sort of all look like this. Now that's just the sp3s. What about these other 2 hybridizations? What do these look like? Well, if you combine the s orbital and only 2 of the p orbitals, you can get 3 new hybrid orbitals. We call those sp2 orbitals, and they would each have 1 electron in them. But then there's one other unhybridized p orbital with 1 electron in it, and it's this p orbital that lets us form the pi bond, because remember, a double bond is 1 sigma and 1 pi, whereas every single bond is a sigma bond. And then there's one other. That would be from the combination of 1 of the s orbitals and only 1 of the p orbitals. You get 2 new hybrid orbitals that are called sp, and that leaves you with 2 unhybridized p orbitals with 1 electron in each. So when you have an sp2 system with that extra p orbital, you can form 1 pi bond, but if you have 2 leftover p orbitals, you can form 2 pi bonds. And we could look at any of these molecules and explain all the orbital overlaps that we get. Here's a sigma. The middle one is actually a sigma and a pi. I will label them separately. Here's another sigma, and here's another sigma over there. And we could even talk about which orbitals are involved in all of this overlap. Well, hydrogen is just bringing its s electrons, so those are just s orbitals. The carbons, well, the carbon has hybrid orbitals, and it has 3 of them. It has 3 hybrid orbitals in this case, each of them capable of forming a sigma bond. And then there's one other unhybridized p orbital, and that's where the pi bond comes from with the other carbon. So then 3 sp2 orbitals in this carbon, and there's everything. So we have a sigma made out of an s and an sp2. We have another sigma made out of a different s and an sp2. We have another sigma made out of 2 sp2 orbitals, and we have a pi bond made out of the 2 p orbitals. So we can track every single orbital, hybrid or not, and assign it to every single bond that's formed. All you really need to know, though, is what type of orbitals, what type of bonds are found in what types of bonds we see in our molecules, and which orbitals can do what. P orbitals only do pi bonds, hybrid orbitals and s orbitals can do sigma bonds. That's it, and that's going to be true for all the molecules that we look at. So I started off by saying this helps us explain the energy and lengths of bonds. So how do we visualize that? Well, think about what a bond looks like as atoms start far apart and get really close to each other to actually form a bond. When they're too close to each other, there's a repulsion between protons and protons, or electrons and electrons. When they're really far from each other, there's attraction between protons and electrons, or electrons and protons. So there's an optimal distance right there. That's your optimal distance. And that's called the bond length. So in this potential energy diagram, we have our bond length right here. It's the lowest point. And this is just an arbitrary picture of where the carbon-carbon double bond might be. And all you really need to know is that that dip is the most important part, and the distance along the x-axis, that's the length, and the dip down from the central y-axis correlates with the strength. So, relative to those two measurements, where would we put a single bond and where would we put a triple bond? Well, let's start with the triple. A triple is going to be stronger and shorter than a double bond. So if it's shorter, my potential energy trough is going to be somewhere at a shorter length, but it's going to be stronger, so it's going to be deeper. So let me actually highlight the carbon-carbon double bond. And the triple bond, I'm going to make a slightly different color. It's going to be shorter, but stronger. And the only part that matters is where that trough is. So this is a shorter length, but a stronger dip. What about the single bond? Well, the single bond is going to be the opposite. It's going to be longer and weaker. So it's not going to dip down as much, but it's going to be farther along the x-axis. So there's our single bond, and there's our triple bond. And this is just a common diagram that's used to show the length and the strength of bonds. However, not all bonds are created equal. This is a typical carbon-carbon bond and a typical carbon-carbon triple bond, etc. But sometimes we get different types of carbon-carbon bond character in the same molecule. And this comes up because of the delocalization of electrons that we see in resonance structures or resonance contributors. Resonance contributors show how electrons are actually not localized and they're shared by more than just two atoms. You often think of a pair of electrons in a bond as being shared by just two atoms, but sometimes one lone pair of electrons, or not lone pair, but could be shared between multiple atoms. as they are connecting a set of them. So we see this anytime we have pi bonds and lone pairs, and it means there's more than one way to draw a valid structure. So sometimes one Lewis structure is not sufficient. I'll show you what I mean. So here is the molecule nitrous oxide. Nitrous oxide is 2 nitrogens in a row, and then the central one's connected to an oxygen. And if I try to use up my valence electrons, we come full circle. 2 nitrogens plus an oxygen would be 16 valence electrons. I have to use them all. So far, it looks like I'm only using 4. Let me do what we did a couple of lessons ago and just fill in the octet. That would be 2, 4, 6, 8, 10, 12, 14, 16, wait, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I don't have 20. I only have 16. So I have to take away a pair and share an extra bond. And then I actually have to take away another pair and share an extra bond. And what that gives me is one valid form of N2O. Now I have 2, 4, 6, 8, 10, 12, 14, 16. That is a valid way of drawing this molecule. However, it's not the only one. You could also show this molecule as an N, and an O, but instead of a double and a double, it could be a triple bond on one side and a single bond on the other. And that's just as valid. That would give me 1 lone pair on the left nitrogen and then 3 lone pairs on the right oxygen. These are both correct. These are both okay. You'll actually learn later about formal charges, so I'm going to slightly introduce that right now. This one would have a positive nitrogen. This one would have a positive nitrogen and a negative oxygen. And, this one would have a negative nitrogen. So between these two contributors, it turns out that negatives prefer to be on more electronegative atoms. So this is better, but they're both valid. In fact, there's even another one that we could draw. There is a third one that has a nitrogen-nitrogen single bond and a nitrogen-oxygen triple bond. That would give me 3 lone pairs on the left nitrogen, 1 on the oxygen, formal charge of plus on the middle nitrogen, plus on the right oxygen, and -2 on the left oxygen. Notice it always adds up in this case to a net of 0. This would be the worst of the resonance contributors because there's so much charge. The better one had a negative on more electronegative atom. But they're all valid resonance contributors. All 3 of those count. The most common example of resonance is certainly the molecule benzene. If I were to draw benzene, it does not have carbon-carbon single bonds. It's actually a carbon-carbon double, and then a single, and then a double, and then a single, and then a double, and then a single. But there's another way to draw this that looks almost the same. It's still a hexagonal arrangement of carbon atoms, and each one has 1 hydrogen attached. But instead of this bond in the upper right being a double, it's a single, and instead of this one in the lower right being a single, it's a double, and likewise. And you separate them with a double-headed arrow. You might be going, wait, aren't these exactly the same? No, they just have equal contribution. And what that means is that the carbon-carbon bonds are actually all the same. CC bonds are all the same here. They are in between a single and a double, because that extra pair of electrons that's forming that pi bond is shared between more than just those 2 atoms. It is delocalized throughout, frankly, the whole molecule. So I'd like you to hit pause, absorb that for a few seconds, and then see if you could come up with at least one other contributor for the ozone and the diazomethane molecule. Start by just modifying the template and turn it into a valid structure, and then come up with a second structure that would be valid with the same electron count. Try that now. Okay, so for ozone, ozone needs one double bond between the oxygens. That'll put 3 lone pairs on one of the oxygens, 1 lone pair in the middle, and 2 lone pairs on the other side. There's another contributor that looks just the same, but it reverses the placement of the single and double bond. So what that means is that all the oxygen-oxygen bonds are identical. It's exactly between a single and a double. It's exactly between a double and a single. So each of them is like a 1.5 bond. In fact, that's called a bond order. Something similar happens with the diazomethane molecule. You can have a carbon-nitrogen double and a nitrogen-nitrogen double. That would put a lone pair on the... Oh, no, that wouldn't put anything on the middle nitrogen. That would put 2 lone pairs on the nitrogen out there. Alternatively, you could have a single carbon-nitrogen bond and a nitrogen-nitrogen triple bond. That would give you 1 lone pair on the carbon and 1 lone pair on the nitrogen. Going back to formal charges, just to finish up, we actually do have formal charges here. The middle nitrogen would be plus in both cases. The left one would have a negative nitrogen. The right one would have a negative carbon. And that means the left one is better because the negative is on the more electronegative nitrogen. There are formal charges in the ozone molecule as well. A negative would be on the singly bonded oxygens, and the positive would be on the centrally bonded oxygens, but these are equivalent resonance contributors. There's no difference in them in terms of their stability. Okay, so that's a lot of information about how to draw resonance contributors. They're essentially more than one valid structure where all that's different is the placement of the electrons. The connectivity of the atoms is the same. A quick tutorial on how to look at these bond energy diagrams. The deeper it is, the stronger it is, and then the farther along the x-axis, the longer the bond. And a lot of this has to do with hybrid orbitals. Atomic orbitals hybridize so that we can form pi bonds from our unhybridized p orbitals and very strong sigma bonds from our hybrid and s orbitals.